So now we are coming to uranium-thorium dating, which always is difficult to plan to present, because I know for some of you it will be totally boring. For others, I hope it will be also interesting. What I mean is basically everybody doing Speleothem research sooner or later will come across the question of chronology, and most likely will at least try uranium-thorium dating. So most of you who are in the field probably already was in contact with this method. However, I still decided to go into some of the basics. Just this is the summer school, and for those who are new to the field, we should probably all be up to speed with the basics. And then in 30 minutes, I decided to skip the measurement and preparation parts in the clean lab and focus on more hands-on questions that apply to pretty much everyone for subsampling for uranium-thorium dating. And then the question that buggers most of the samples, you hardly any have completely clean samples. So what can we do about a detrital contamination? Right, right into the basics, very brief and quickly. So we are talking about uranium-thorium dating, and that requires uranium. That's the element in the actinide series. It's one of the heavy elements down here with 238 neutrons plus protons. So it's very heavy. And uranium is radioactive, as probably everybody knows. And what's special about the activity of uranium and also 232 thorium is that it's a start of a so-called chain. So it's a decay chain, which means it's not a simple mother-daughter radioactive decay, but uranium decays via a lot of intermediate decay products, and each of the products again is radioactive. So it's a product and a radioactive mother to decay to the next decay product, and so on until an end member is reached, which is lead, and that will be the topic of the next talk, because uranium provides two possibilities for dating. And now we focus on the first part of this decay chain for uranium, which includes uranium-238, which includes 2 uranium isotopes and thorium. The 2 intermediate ones are very, very short-lived. However, where there's uranium in an old rock, and this decay chain is in what we call an equilibrium, you will find all the elements that are part of this chain. So here's the list of the complete elements. So all these elements will be in this rock. Some of those, however, at a very, very small proportion. So what does the equilibrium mean that I already mentioned? And radioactive equilibrium in the decay chain means that all the elements that are part of the chain basically are in a steady state in terms of how many of those are produced by decay of the mother and how much is lost by decay to the next element. So that means that the filling buckets of all these elements here stays constant as soon as radioactive decay is reached. So what comes in goes out. The only 2 that change in time in this steady state is the starting element, and then of course the ultimate lead. This bucket fills up because there's no escape via decay. So what we really need is uranium in our samples. How the clock works I'll come to, but uranium is actually quite an abundant element. So in the upper crust, value of around 1.7 ppm is normal. Of course, that's an average, but that means that uranium is pretty much abundant in any rock. And that also means that we do find it in most of our speleothems, which is one of the key prerequisites that we can actually use this element for dating. But how does it get into our speleothems? So how is it connected? Okay, we do find uranium in the rock. And I had to use this figure because it's from one of the pioneering works of uranium stereostating of speleothems from the 1970s. And what's happening is that usually uranium is not soluble in water, and that's depending on the oxidation state it's in. It's usually 4+, but weathering actually can change the oxidation rate of uranium. It oxidizes to the oxidation state +6, and then it's soluble in natural waters. So then runoff water or water percolating through these rocks can dissolve that uranium and carry it with it. So this is, and it's ending up, for instance, in the oceans where you do find uranium, but it also will be present in the water that percolates our system in karst areas. So when we go to part of a figure provided by Ian and Andy, when we have the allergenic water, this can already have traces of uranium that's leached from the rocks. And then another effect happens that we all know when we go to this arrow in a bit more detail, and we have a very tiny fracture that's filled with percolating water. It's going to be CO2 enriched, and then it forms carbonate by bicarbonate. And we have the dissolution effect that this water is acidic enough to dissolve the limestone. But when that happens, whatever is in the limestone can also end up in this water. So we have uranium typically in the limestone. We have trace elements. So I just used magnesium as an example. And all these are ending up in the water. And the same happens to thorium. And thorium is there because there's uranium, and thorium is one of the decay products. So the decay product, 230 thorium, is in the host rock, and it would be dissolved. However, thorium hates to be in solution. In this natural water, it's not sustainable. So what does it do? It escapes to any surface it can find. So it sticks to the surface of these fractures, which acts as if it filters out all the thorium. So when this happens, what's ending up in the drop that enters the cave and degasses and forms stalactite, or when it falls onto on the ground, a stalagmite, basically contains uranium, the trace elements, of course the calcium, but no traces of thorium. So, and that's the key for our dating method. We have what we call a chemical fractionation. Uranium and thorium, two different elements, are very different in solubility in natural waters. And we use that these can contain dissolved uranium, but no thorium. And then, of course, what's end up in the stalagmite is that only that's delivered by the water. So what does it mean to our decay chain in the stalagmite that just formed? So if it was old, we would have this decay chain here in equilibrium. But due to the chemical fractionation, this bucket is emptied. So no thorium comes there. We have the uranium at the start, but this bucket is empty, so the decay chain is interrupted. But we have the uranium. Uranium is radioactive and decays, and this then starts slowly filling up this bucket again. And the filling process depends on the half-life of the element or the isotope 230 thorium that's filling up. And it takes about 5 to 7 half-lives to fill. After 7 half-lives, we have a bit more than 99% filled, and that takes 530 years. So this is typically the time we reach out with uranium-thorium dating. It depends on measuring precisions, whether you can still distinguish from 100%, whether you can actually go for 8 or 9 half-lives. So you need to be very precise in measurements. But typically, one would say after 7 to 8 half-lives, game's over, and then you have to look for another method. Right. So what we need to measure is the amount of 230 thorium relative to what's there in uranium. And we know exactly the half-life, and this should follow an exponential saturation function like that. And if we measure today the 230 thorium relative to uranium, we can work out the age of the sample. So that's the basics, how it works. And what we need to consider is that in practice, of course, this ingrowth is not as simple as that. This is for the two uranium isotopes being already in equilibrium, then it looks like this. But if the two uranium, 234 and 238, that are part of the decay chain are fractionated, so here we have an activity ratio starting point of 2, then this also tends towards the equilibrium following the half-life, and then the ingrowth of 230 thorium follows this curve here. So in practice, we need to measure both the 230 thorium and 238 uranium, and also the activity ratio of the two uranium isotopes. And with these two, we can always work out the age. However, whatever we calculate in the lab and get from these samples is only the real age of formation for these samples if at start there was really no thorium. And this is very important. The other one that's important is that our clock was not messed up by any effects in the cave. So that means we call it a closed system, that uranium was not mobilized from the stalagmite, or less likely that thorium has been added or removed. But since uranium is soluble in waters, of course, it's possible that something happened to uranium even after stalagmite formed. And these two preconditions are extremely important, and you have to convince yourself and others that this was not the case, or if you do find initial thorium, then you need a way to correct for that. So if everything works fine, this is what you aim for. So here are two examples. This is from the 1975 work by Hoffmann et al. So here you find the distance and then the age, and what we would call an age model with point-to-point linear interpolation. And here a benchmark publication by Hai Cheng and colleagues more than 10 years ago now. With a state-of-the-art precision that you can achieve. Difference between these two studies is here. In 1975, it was done via alpha spectrometry, the measurements, larger samples, larger uncertainties. And this study here is with multi-collector ICP-MS, state-of-the-art, with even sub-per-mil precision on the ages. The basics here are exactly the same. The difference is the analytical precision that really did quite a bit of progress since 1975. So I want to focus on the sampling, because how do you derive an age model like this? Well, you need subsamples from your stalagmite from various positions, and you need to run it through a chemical separation, a preparation procedure, and measure it either alpha spectrometry or mass spectrometry. But I think that taking the sample is a very, very important step. And this here is one of my key things that I would like to highlight. Start with a good plan. If you are so excited with your style that you want to just go and know what the age is, and you drill as many samples as you can think, and at some point you find out, oh shit, I also need to have space for stable isotopes. I want to do trace elements, maybe clumped isotopes. Yeah, then how to do this? So please start planning this before you do sampling. Vice versa, if you start with some stable isotopes, leave some room for dating, because this is what you ultimately need. And each step document as thoroughly as possible. I think that most of the hiccups and problems of mismatching records are linked to the problem that maybe proxy records are not properly aligned with the positions of the dating samples, and even millimeter mismatches can then end up in hundreds or even thousands of years, which are not analytical uncertainties. It's just that it has not been linked because the information might not be present. So this is, if you take that home, this will save you a lot of time when you want to publish and you find out, oh shit, something's maybe not wrong, but I can't tell what. Okay, once you come up with a plan, you need to sample. That can be relatively simple. So there's the good old drilling. I recommend always use a clean environment. This is HEPA filtered air here, because any dirt you mix into your samples here will end up in the sample and then be a bugger for the analysis. However, you can use a drill, and then on a polished cross-section, you can identify layers. Here in this section, then with a drill bit, ideally uranium or thorium-free, you can drill a sample. This is roughly a 20-30 milligram sample. This is a bit more. So this is typically what would be appropriate for dating. And please try to stay within growth layers that you can see, and try not to get across any visible hiatus or dirt layer. So that's one thing. Another possibility is to cut up the specimen. So if, for instance, you want to do a combination of radiocarbon and uranium thorium dating, here small wafers were cut. For this, the whole thing was cut up in slabs, and then small wafers were cut, and the corresponding slabs then were used for stable isotopes and trace elements. And if you document that well, then you can all get them on the central axis here in the middle. Of course, you can also do a combination, start with first data for dating with drilling samples. And if you find out, for instance, here in this section, there's something going on, I want initial dates, you can cut a slab. This is the same in big, cut in with a wire saw and get small samples out. It's both fine. Pieces are easier to keep clean prior to your preparation in the clean lab. As I said, with a powder, you drill one and any dust gets in, you will never get this out again. So other than that, there's no advantage or disadvantage. But for initial samples, because it's less destructive to the specimen, I would always start with drilling samples. But before you go for all the samples, if you think, oh, I need 25 because it's 50 centimeters long and I want a date every 2 centimeters, please start with initial data, just two, bottom and top, or near bottom, near top, because the ideal sample size depends on the uranium concentration and the age. And both information you will get, at least for these two samples, from these two results, because you can have an expected age range, and the uranium concentration, of course, can vary within a stalagmite, but you have the ballpark, whether you are in the nanograms per gram or whether you have a Spannagel with hundreds of micrograms per gram. At this point, I want to highlight that if you drill a small core prior to sampling, so one here from the bottom, and you scrape off a small sample from the top, before you take out a stalagmite from the cave, this is good to see whether the stalagmite fits the bill and you want it. So you do not take it unnecessarily, but also you already have that information here and you can then start straight away. So it's a double benefit. Okay, and then after you've got the initial dates, then you have to identify the best positioning for your samples, and you should work along growth horizons, see whether there are potential hiatuses that you need to constrain with close ages. And of course, ideally you stay with clean calcite that minimizes hiccups with contamination. Right, so how does it go? So we would start with a bottom and top, and then the question is, how many dates do you need? That's always a good question, and I don't have an answer. It depends, because it depends on how linear or how well your continuous your stalagmite formed, whether there are many hiatuses, whether there are cleaner or dirtier section, and unfortunately on your funding and access to a lab. I mean, this sometimes restricts how many dates you can process. Anyway, so after bottom and top, you should start with some samples to fill in, can be anything between 3 and 5, which at start I would choose more or less equidistant or based on hiatuses. And then you can start filling in gaps. And you see that what here could still be a linear growth. Now, okay, you see, okay, there's something happening down here. This could leveling and be something like a plateau, maybe also here. This is now overdone. This is just if you have the luxury of direct access to a dating lab. So you wouldn't need that many samples down here, because 3 or 4 would be enough to confirm that between the start here and the end here, it is pretty much constant growth. But wherever growth rate changes, you would need more than one date to confirm that it's actually here changing from a slower growth to a faster growth somewhere here. And if you used, for instance, stallage, which Dennis Scholz probably presented 2 weeks ago, a minimum of 3 dates would be needed for each growth episode. So this is, if you have a single date, for instance, up here, then stallage would ignore it, more or less. So you would need at least 2 more so that it will be sufficient. So if you had 5 or 6 growth horizons or growth phases, for each one, a minimum of 3 days would be required. Okay. Sample size. The sample size, of course, then defines also how many samples you could take, because you would need the space for those. And again, for the sample size, it depends. And it very much depends on the uranium concentration. So I used this example from Hai Cheng et al. The stalagmite, they gave the information. They measured it on the mass spectrometer with an intensity of about 300 volts of 238 uranium. So I back calculated this with the specs for Neptune Plus here. That means they ran probably a solution with 200 ppb, 238 uranium. And if you use typically 1 milliliter of that, you need a total of 200 nanograms uranium. And with a concentration in this stalagmite of 600 to 1,000 nanograms, sample size would have been between 200 and 400 milligrams. So 100 times more what Nele just mentioned for the clumped isotopes. It's a verbal sample size. For me, it's quite large, but that's still fine. But if you go for a stalagmite that's probably more familiar with most people, having something like a few hundred nanograms per gram uranium, and you want the same exercise, then you find out if you go for sub per mil precision, as if Hai Cheng, you need 2.5 grams of that sample. That's a cubic centimeter. So that's 1 centimeter, 1 centimeter, and also drilling down 1 centimeter. If you place that on the stalagmite, well, that is a lot of material. And this here, that would be a typical sample of 25 milligrams. That still gives you 5 per mil precision, not 0.5 per mil, but you can really place this within a growth horizon. And then what you always need to ask yourself is, what is probably my expected growth rate? So if I used this growth rate of 0.005 millimeters per year, then the sample size here for sub per mil precision would cover 2,000 years. And it's nonsense to have a 20 years precision on an age of a sample that in itself covers 2,000 years. So what you would aim for is something like this, where A, your analytical precision is in the range of 200, 250 years, and what your sample covers within 1 millimeter is identical, so that these two uncertainties are in the same ballpark. So this is, of course, you need first data of your sample to find out what you expect, and then you can calculate at what point a larger sample does not really improve anything in terms of precision. Right, so now to the biggest bugger that we usually have. I think I have not too much time left, but that's the Detrital thorium. And we have to make sure that there is no thorium present at time. And if we go to some specimen, you see clearly by eye, this is not always the case. Here it's clearly with sediments, or here you have these reddish layers that probably were dust layers when the stalagmite was dry. And so how can this come in? Well, this was our ideal case scenario, but unfortunately, it's not always like that. Sometimes very small particles can find the way through this, through fractures that are wide enough. So this could be any particles, and those particles themselves can contain uranium and thorium. That's one thing. But the other thing is that the thorium escaping to the surface here can also happen like thorium escaping to the surface of these particles. Or other taxis, so to speak, for thorium can be so-called colloids, which are also very frequently appearing in the water column. So with this, thorium has a means of transport, and that means that gets into the drop, and what gets into the drop ends up in our stalagmites. And another source then is like this red layer that I showed on the specimen here. You could see this stalagmite in a dry cave today. It was covered in red dust. You cut it open, you find this red dust also inside. So there's also airborne particles that came not in through the water. Or this is a stalagmite found in sediments, and it formed on top of these gravel sediments. And while it formed, it was permanently probably covered with parts of the sediment and included those. And you also find this in caves that are frequently flooded, that sediment particles are left behind on the top of stalagmites. So we have a range of transport vehicles, and they are all a bit different. So the particle in the water has the composition itself, so it can have uranium inside and thorium inside, and it absorbs thorium from the water. Airborne particles have just their own composition, and the colloids basically are only the taxi and don't bring their own signature. And the problem is that we have these, they all have a slightly different composition, and we cannot have just a single one, but we can have the composition with a combination of detritus particle, colloid, or also then additional airborne particles. And that complicates the picture because basically every stalagmite we do find even very, very slight traces of 232 thorium, and that is the indicator that we have a contamination. And as soon as we do find that, we are looking for, if we find that, how much of the 230 thorium was coming with it. And this is then the important information that we need to find out on our sample to get a way for a correction. Okay, and for a correction, what you do is you can either try to see for a particle, do a so-called isochron. What does it mean? So here I mimic this, having a solution that was a dissolved, very clean stalagmite with almost no 230 thorium, and 7 fractions of that. On each of those received a small sample of a basaltic rock. So that was particle-only contamination. And when you analyze this, you put it through chemistry, the signature of the rock gets into the samples. And what you see here is the more 230 thorium is in the sample compared to uranium 238, also the more 230 thorium we find. So we have this relationship. And what we can do here, we can, the slope gives us how much thorium 230 was coming together with the 232. And we can back extrapolate this to 0 and then find our sample, our initial. And if we do this with this sample and we calculate initial or ages for the individual samples, we would have an age range like this. But if we did this on this isochron, then we have identical ages between the isochron and what I know for the reference solution. It works in practice. So on this dirty stalagmite, this was done on 5 samples because there was no more space for 7. And you can do the same thing, but it never looks as perfect as the one I produced in the lab because there can additional effects. But we have this isochron here, and we could then define an age up here for this layer based on the isochron. And then here, down here, we took a single sample and corrected it with a so-called bulk earth value, and that is what we expect for a common crust particle to be a contamination. And the nice thing about these isochrons, these also tell us what the factor is for our samples. So I could calculate the detrital number for our stalagmite, as was 0.78, and the bulk earth that is commonly used is 0.8. So they are actually identical. So the method works. But we do not usually have particle-borne detritus. So this is actually very clean calcite with traces of 232 thorium. And here you can also get isochrons, and they do not behave as nicely. And why is this? Because the effect is much stronger and probably much more variable. And we have these initial values that are up to 10 times more than what you would expect for bulk earth. And here the problem is that here we can have variable, so different colloids, for instance, bringing in different compositions. So we do not have one defined composition for this kind of contamination. And this is why the uncertainty of these correction factors is typically quite large. Just to end, there are 2 more ways to get this correction factor. One, if you're really lucky and you have a stalagmite that was actively forming when you took it, then you can actually get ages to the very top. And if that is the very top sample is like present day, then you can use the thorium-230 you find in that sample as the marker for what was brought in, not by decay, but just by when it formed. And then you can use this to correct all the other ones. Here, the 230 thorium to 232, if that's a small value, then this indicates typically a high degree of contamination, and you see the ages for those go off. But a modern sample can also give you an idea about this factor, or what John Hellstrom suggested in 2006, where you do not have modern overlap, you can still see which samples are out of stratigraphic order, and then do a Monte Carlo modeling with which correction factor you bring all of those back into line. However, this of course assumes one correction factor being the same for all horizons, which is not necessarily the case, because here, if you do this exercise, they are, at least in the mean, different. However, if you use the uncertainty of that, they are all the same. Okay, I don't have more time to go into this. I could talk hours about this, but I leave it to you to ask questions.